Hi everyone. So I've given an iteration of this presentation previously, but there are some pretty new results that have quite a significant implication, not only for understanding the timing of mineralisation at the Great Bear property, but also for the chronology of events in the Red Lake Greenstone Belt. So this research is, or this presentation is essentially an update of the research currently being conducted on the Great Bear deposit, but also the implications of that research. And fundamentally, this wouldn't be possible without the support of NSERC, Great Bear Resources, and especially Kinross, who have provided a lot of financial and logistical support. So the Red Lake Greenstone Belt is located in northwest Ontario, up in the Uchi subprovince. And it's one of 6 major greenstone belts of the Uchi subprovince, and it records 300 million years of volcanism, intrusive magmatism, and sedimentation. And it's also one of the largest and richest orogenic gold camps in Canada. Most notably, the Campbell Red Lake gold deposit has produced in excess of 15 million ounces of gold in its lifespan. So exploration and mining in this greenstone belt has largely prioritised the so-called mine trend, which is basically a corridor of east to southeast trending D2 structures between the towns of Kochna and Barmertown that formed during the 2720 to 2715 million year Uchin phase of the Kenora orogeny, and that's broadly related to the amalgamation of the Winnipeg River terrain to the south and the North Caribou terrain to the north. Now, gold mineralisation within this mine trend is principally hosted by tholeiitic and komatiitic metabasalts of the 2.99 billion-year-old Barmer assemblage, which is the oldest established metavolcanic assemblage in the Greenstone Belt. Now, the recent discovery by Great Bear Resources of the Great Bear deposit is quite significant, in part because the deposit is located 25 kilometres to the southeast of the main Red Lake camp, but also because mineralisation is predominantly hosted by felsic porphyries, not metavolcanic rocks of the Barmer assemblage. So this is a simplified geological map of the Great Bear property, and broadly speaking, it consists of 2 domains, known as the mafic domain to the south and the felsic domain to the north. And these are separated by this so-called LP fault, which is a structure that was identified as part of the WS2B lithoprobe seismic surveys done in the early 2000s. And 3 zones of mineralisation have been identified within these domains. And this includes mineralisation associated with quartz veining in the limb and hinge zone of the mafic domain, as well as disseminated and vein-related gold in the felsic domain. Now, historically, exploration across the property has largely targeted the limb and hinge zone due to the similarities in the style of mineralisation with the main Red Lake camp. And it wasn't really until 2019 when Great Bear Resources decided to drill the felsic domain. And in doing so, they discovered that there was widespread, relatively shallow, disseminated gold hosted by variably altered felsic porphyries. So previous geological mapping of the property basically suggested that the stratigraphy in the felsic domain, which hosts much of the established mineralisation, was actually part of this so-called McNeely sequence of the Confederation assemblage. And this dates to around 2748 to 2742 million years. And this is quite significant because the Confederation assemblage was largely thought to have been barren in terms of mineralisation. However, there were no real isotopic constraints from the felsic domain at that time to support such an attribution. So one of the key parts of our research was to ultimately address whether the felsic domain was in fact part of the McNeely sequence of the Confederation assemblage. And so to do this, we first needed to establish the stratigraphy, which involved extensive core logging and the documentation of important textures and facies relationships. And these observations ultimately formed the basis for the sampling of the metasedimentary deposits, as well as the felsic porphyries, which host mineralization, ultimately for zircon dating. So this is a more detailed geological map of the Great Bear property. And broadly speaking, the stratigraphy in both the mafic domain as well as the felsic domain is highly strained, with the main foliation trending northwest-southeast, although the orientation of that foliation does vary along strike of this geophysically interpreted LP fault. There's very little outcrop across the property, but a lot of drilling has been conducted by both Great Bear Resources and now Kinross, that it is possible to reconstruct the stratigraphy of the felsic domain. So extensive core logging of some representative holes from across the felsic domain has basically identified 6 key lithofacies. These include 3 metasedimentary units, 2 variably altered felsic porphyries, a fragmental unit that's sort of more of a volcanoclastic deposit, and all of these deposits are variably intruded by mafic dikes and sills. So just starting at the base of the sequence, adjacent to the LP fault, we have a very highly strained sequence of sericitically altered fine-grained sediments. This is overlain by a second metasedimentary unit called MS2, and this unit consists predominantly of massive to thinly bedded fine-grained sediments with garnet, staurolite and andalusite porphyroblasts. The top photo here is sort of somewhat representative of the metasedimentary 2 sediments. We have lots of garnet, extensive sericite domains. These thin section images of the matrix of the sediments consist predominantly of quartz and biotite, and the biotite wraps and deflects around the major garnet porphyroblasts. And in this bottom photo here, we have a felsic porphyry of E31, and I'll discuss that in a second. That's intrusive into metasedimentary unit 2. So both metasedimentary unit 3 and metasedimentary unit 2 are intruded by felsic porphyries, which have been termed E32 and E31. Now, E32 is generally white to grey in colour. It's often albertized and often generally aphanitic to mildly porphyritic, while the quartz feldspar porphyry of E31 generally consists of these distinct white feldspars with blue-grey-white quartz phenocryst or quartz eyes that are hosted within a fine-grained ground mass of quartz, feldspar and biotite. And another key question we were trying to address was whether the E32 porphyry, that's the altered porphyry, was genetically related to the quartz feldspar porphyry of E31. And what's clear from extensive core logging is that the contacts between E31 and E32 are generally extremely sharp. So essentially what we can see, or what we interpret, is that the E32 porphyry was in place first. It was subsequently albertized, and that was followed by the intrusion of the E31 quartz feldspar porphyry. And then towards the top of this sequence, we have a so-called fragmental unit, which is essentially a poorly sorted, matrix-supported volcanoclastic deposit. It consists of sort of half-centimetre size quartz and feldspar crystals. Often there's also larger angular to round quartz feldspar porphyry fragments. Now these fragments within this deposit are essentially interpreted to have been derived from the E31 porphyry itself. Now this unit is overlain by, or often actually interbedded with sediments of metasedimentary unit 1. And these sediments are generally thinly bedded, fine to medium grained, but there's also rare graded bedding that would indicate sort of a northeast facing direction. So that's to say the sediment's young towards the northeast away from the LP fault. And you see in this top image here, this fragmental unit is interbedded with MS1. And in this part D photo, we have a distinct sort of quartz feldspar porphyry fragment that's hosted in a sort of finer grained ground mass, or matrix in this case. So in terms of the temporal evolution, we basically envision that we We had the early deposition of metasedimentary unit 3 and metasedimentary unit 2, possibly in a structural basin. We then had the emplacement of the E32 porphyry. That subsequently underwent albertization. We then had the intrusion of the quartz feldspar porphyry of E31. It's likely that that E31 porphyry possibly also erupted at the surface, producing a lava dome. Subsequent quench fragmentation, autobrecciation, and possible collapse of that submarine lava dome resulted in the ultimate formation of the volcaniclastic deposits of F1. And then we also had ongoing sedimentation producing metasedimentary unit 1. And it's also worth noting that the entire stratigraphy is sericitically altered, so that event likely occurred after the emplacement of MS1, followed by deformation. So one of the key questions we were trying to address, again, was whether this sequence was part of the Confederation assemblage. So initially, we conducted detrital zircon geochronology for 3 samples from the metasedimentary deposit sequence, so MS3, MS2, and MS1. And what we see is that each sample has a distinct cluster at around generally 2720 to 2730 million years. MS1 has a series of older ages with a peak of around 2900. But for all intents and purposes, the maximum depositional ages for these sediments are around 2720 to 2715. In an effort to better constrain the ages of the host rocks that host gold mineralization, we also attempted to date an exposure of the E31 quartz feldspar porphyry, which also intrudes the metasediments. And initial results basically suggested that the porphyry had a crystallization age of approximately 2722 MA. However, Mike Hamilton was able to do additional analyses of 4 more grains, and he was able to basically demonstrate that the porphyry had a much younger crystallization age of 2710. And this age has been supported by dating additional grains from the exact same sample using laser ablation ICP-MS at Laurentian University. But ultimately, this data suggests that the stratigraphy is not part of the Confederation assemblage, but rather part of a much younger suite of felsic porphyries and intrusions, most likely related to the St. Joseph plutonic suite. So this new age has quite significant implications for understanding mineralization in the Greenstone Belt, because in a 2004 paper by Benoit Dubé, he basically suggests that the main stage of gold mineralization at the Red Lake mine camp, in this case here, basically occurred between 2723 to 2712 MA, and that most likely coincided with the Uchin phase of the Kenora orogeny. He also suggested that there was a late stage gold mineralization event that was associated with D3 deformation and metamorphism after 2702. Mineralization was also envisioned by Chi to have basically been derived from CO2-rich fluids from the mid to lower crust, at least with respect to the main Red Lake camp. And in fact, the MT survey across the Red Lake Greenstone Belt provides some evidence to support this. It's like we have this big, strong conductive finger that again extends from the mid to lower crust up to the surface expression of the Red Lake mining camp. And we also have this discontinuous conductor beneath the Great Bear deposit. Now, our new age of 2710 for the E31 porphyry at the Great Bear deposit, which hosts mineralization, is younger than previous established ages for D2 deformation and mineralization in the main Red Lake gold camp. So this would suggest that there's either that D2 deformation extended for longer in the southern part of the Red Lake Greenstone Belt in the vicinity of the Great Bear deposit, or that mineralization was associated with D3 deformation. So research at the Great Bear deposit also involves research by 2 master's students and a PhD student. So Maggie is currently in the final stages of her research on the structural evolution of the property and will likely submit this upcoming summer. Jolene started approximately 6 months ago in the summer of 2024, and she's looking at metamorphism across the property. And Vierland started approximately 1.5 years ago, same time as Maggie, and he's doing his PhD looking at mineralisation and gold remobilisation. And they all have posters at PDAC, so if you're interested in learning more about their work, they'll be presenting at the Metro Toronto Convention Centre. So I'm just going to present some of Maggie's results. She's done an incredible job characterising the styles and relative chronology of deformation across the property. And she's also been able to provide important uranium-lead age constraints for deformation and mineralisation. So in an attempt to constrain the duration of deformation, Maggie basically conducted detailed outcrop mapping of a number of exposures across the property. And this included a series of relatively undeformed granites that intrude highly deformed mafic volcanic rocks. Now, these granites were sampled at a number of exposures, essentially as the basis for uranium-lead geochronology, ultimately to constrain the minimum age for deformation and mineralisation. Now, the zircon analyses for all of these samples indicated a high degree of alteration, and in fact, probably 80% of the data we had to exclude, but we were able to obtain some reliable ages. So, for example, this sample here from a granitic dike that intrudes the highly deformed mafic volcanics, that yielded an average age of approximately 2692. A second sample, which yielded far more zircon than the other granites and produced a more definitive age group, this produced a weighted mean age of 2695. And then a third sample yielded a couple more ages with an average age of approximately, again, 2695. Basically, altogether, these new ages suggest that deformation and mineralisation occurred between 2710 and 2692 MA. So this sample here is basically the same sample that was analysed by TIMS, and these three samples here were from the granites that intrude the highly deformed mafic volcanics. So just as a somewhat conclusive slide, I thought it'd be good to look at the similarities and the differences between the Great Bear deposit and the Red Lake mining camp. So in terms of similarities, both deposits are located adjacent to major unconformities and faults. Both deposits are located adjacent to sedimentary belts. And both deposits are also hosted within a zone of predominantly northwest-southeast trending structures. But there are some significant differences. So mineralisation at the main Red Lake camp is hosted by the 2.9 billion-year-old Barmah assemblage, while mineralisation at the Great Bear deposit, in the felsic domain at least, is hosted by felsic porphyries that have an age of approximately 2710 million years. Mineralisation in the felsic domain is predominantly disseminated and shallow, while gold mineralisation at the Campbell Red Lake deposit is associated with quartz carbonate veins. And finally, mineralisation at the main Red Lake camp was likely associated with the 2723 to 2712 Uchen phase of the Kenora orogeny, while mineralisation at the Great Bear deposit was associated with either a late D2 event or early D3 deformation between 2710 and 2692 MA. So ultimately, this new deposit does open up the possibilities for greenfields exploration for some of these more atypical or unconventional type gold deposits. And thank you. If anyone has any questions, I'm happy to.